Welcome back, folks, guys and gals. This is Greg Silverman, your Chief Investment Officer, for another session of Come Learn With Me. This is part of our Rare Earth mini group special. You want to know what mini groups we follow? Check out the links down below, some particular investment thematics that we follow. Okay, let's read this together. And then if you want to know more details about me and the investment process, you'll catch that at the end. New process could bring rare earth relief. Selective separation, now in development at MIT, has potential to alleviate critical metals shortages. New processing methods developed by MIT researchers could help ease looming shortages of the essential metals that power everything from phones to automotive batteries by making it easier to separate those rare metals from mining ores and recycled materials. Selective adjustments within a chemical process called sulfidation allowed Professor of Metallurgy Antoine Eleanor and graduate student Casper Stin to successfully target and separate rare metals such as cobalt in a lithium-ion battery from mixed metal materials. We just highlight some bullet points. So if you want to skip the article, you can just see the bullet points down below. As they report in the Journal of Nature, their processing techniques allow the metals to remain in solid form and be separated without dissolving the material. This avoids traditional but costly liquid separation methods that require significant energy. The researchers developed processing conditions for 56 elements and tested these conditions, on 15 elements. The sulfidation approach, they write in the paper, could reduce the capital cost of metal separation between 65 and 95% from mixed metal oxides. That will get some attention, won't it? Their selective processing could also reduce greenhouse gas emissions by 60 to 90% compared to traditional liquid-based separation. We were excited to find replacements for processes that are really high levels of water usage and greenhouse gas emission, such as lithium-ion battery recycling, rare earth magnet recycling, and rare earth separation, says Stin. Those are processes that make materials for sustainability applications, but the processes themselves are very unsustainable. The findings offer one way to alleviate a growing demand for minor metals like cobalt, lithium, and rare earth elements that are used in clean energy products like electric cars, solar cells, and electricity generating windmills. According to a 2021 report by the International Energy Agency, the average amount of minerals needed for a new unit of power generation capacity has risen by 50%. Wow, since 2010, as renewable energy technologies using these metals expand their reach. Opportunity for selectivity. For more than a decade, the Eleanor Group has been studying the use of sulfide materials in developing new electrochemical routes for metal production. Sulfides are common materials, but the MIT scientists are experimenting with them under extreme conditions like very high temperatures from 800 to 3000 degrees Fahrenheit that are used in manufacturing plants but not in a typical university lab. We are looking at very well-established materials in conditions that are uncommon compared to what has been done before, Eleanor explains, and this is why we are finding new applications or new realities. In the process of synthesizing high-temperature sulfide materials to support electrochemical production, Stin says, we learned we could be very selective and very controlled about what products we made. And it was that understanding that we realized, okay, maybe there's an opportunity for selectivity in separation here. The chemical reaction exploited by the researchers reacts a material containing a material containing a mix of metal oxides to form a new metal-sulfur compounds or sulfides by altering factors like temperature, gas pressure, and the addition of carbon in the reaction process. Hold on, we need to get some of this in. Stin and Eleanor found that they could selectively create a variety of sulfide solids that can be physically separated by a variety of methods, including crushing the material and sorting different size sulfides or using magnets to separate different sulfides from one another. Current methods of rare earth metal separation rely on large quantities of energy, water, acids, and organic solvents that have costly environmental impacts, says Stin. We're trying to use materials that are abundant, economically, and readily available for sustainable materials separation, and we have expanded that domain to now include sulfur and sulfides. Stin and Eleanor use selective sulfidation to separate economically important metals like cobalt in recycled lithium ion ore batteries. They also use their technique to separate dysprosium, a rare earth element used in applications ranging from data storage devices to optoelectronics, from rare earth boron magnets, or from a chemical mixture of oxides available from mining minerals such as bastnasite. I don't know how to say that. Leveraging existing technology. Metals like cobalt and rare earths are only found in small amounts in mined materials, so industries must process large volumes of material to retrieve or recycle enough of these metals to be economically viable. Eleanor explains, it's quite clear that these processes are not efficient. Most of the emissions come from the lack of selectivity and the low concentration at which they operate. By eliminating the need for liquid separation and the extra steps and materials it requires to dissolve and then reprecipitate individual elements, the MIT researchers process significantly reduce the costs incurred and emissions produced during separation. One of the nice things about separating materials using sulfidation is that a lot of existing technology and process infrastructure can be leveraged, Stin says. It's new conditions and new chemistries in established reactor styles and equipment. The next step is to show the process can work for large amounts of raw material, separating out 16 elements from rare earth mining streams, for example. Now we have shown that we can handle 3 or 4 or 5 of them together, but we have not yet processed an actual stream from an existing mine at a scale to match what's required for deployment, Eleanor said. Stin and colleagues in the lab have built a reactor that can process about 10 kilograms of raw material per day, and the researchers are starting conversations with several corporations about the possibility. We're discussing what it would take to demonstrate the performance of this approach, the existing mineral and recycling streams, Eleanor says. Okay, there you have it. That's very, very interesting, actually, because one of the issues is the monopoly that China has on processing rare earth metals. Guys, I hope you like this. We're investors in this space, and if you want to see how we're investing or where we're investing, check out some of the links below. Again, there's a link to all the mini groups that we follow or curate, basically. There's a link to our investment website where you can sign up and see specific investment offerings. Some in the rare earth space, some in other niche spaces, uranium, gold, silver, etc. And then lastly, if you are a company or a fund that specializes in rare earth metals, we'd like to hear from you as well. We have a special program called Looking Over the Manager's Shoulder, where we can, if we like what we see from what you bring us, that we would be willing to introduce you to our large accredited investor network. So something for everyone. Guys, I hope you enjoyed that. Please like and subscribe, and come and join us again for another session of Come Learn with me. Greg Silverman out for now.